All right, so here we are. It is Tuesday, October 13th, 2020. We're going to first be reviewing a little bit of displaying categorical/quantitative variables based on some of the things that I graded last week and things that I saw. And then we're going to finish section 1.3 with standard deviation. We briefly touched on standard deviation. I showed you how to find it on the calculator. We're going to do an example today and find it by hand. It's not as terrible as it may seem, as long as you stay organized. So we'll see that today, talk about that. But to start, some things from what I graded. All right, first thing, bar graph versus a histogram. Most of us realize that a bar graph has to do with categorical variables and a histogram is for quantitative variables. We seem pretty clear on that. An issue that I saw when I was grading was that people were making histograms that had space in them. The bars weren't together. I know it seems like a small issue. However, with a histogram, the bars should not be separated. Right? Like in the example here, the bars are all touching because we're representing values on that x-axis, on the horizontal axis, which means, like, you know, where one ends, the other one begins right away. There's no space in between, right? Just like on a number line, just where you know, 5 begins and starts or whatever, you know, there's numbers before and after that that are represented, right? There's decimals and all those types of things. So we can't have space. It's just not the way that it works. In a bar graph, we're allowed to have space because where one bar ends, the other one isn't picking up, right? They're separate things. They're not connected by a value, all right? So that's one thing. The other thing was in our discussion board about the categorical variables in the bar graph. A lot of you said that you can describe a bar graph as skewed to the right or having a shape, you know, to be more specific, and you cannot. While it looks like it might have a shape that we could describe as symmetric or skewed, that's false, right? When you're talking about a bar graph and we have categories along the bottom, I can mix these categories around in any way that I want to create any shape. So the shape is not unique, right? So in this graph on our picture here, we have the different fields of study. If I arrange those alphabetically from left to right, I'm going to get a different shape than the one that's on the graph right now. But I'm not changing the data. I'm not misrepresenting it. I'm just changing the way that I'm listing it. But that could change the shape. Right? So with categorical variables in bar graphs, pie charts, things, we can't describe shape. Right? We can't describe center. We can't describe spread necessarily, right? These are all things that I can't find an average for, so I don't have a mean or median, right? Those values don't exist, right? Which means I cannot describe them. You know, I cannot describe bar graphs the same way as I describe histograms. They might look similar. They both use bars. They're both going to have frequency. But because of the type of data they're representing, I cannot describe them using the same characteristics. Okay? So those are a couple things that I saw between the bar graph and histogram questions on our discussion boards. So a bit of feedback. Any questions about that? Okay. Alrighty. Does anyone need a moment to write anything down from this page for their notes? Yes, all right, I will wait. Looks like we're ready. All right. Never mind. Sweet. All right, here we go. All right. Next thing, talking about stem plots. This was having to do with one of the questions on the week 6 CYU about what values you would use on a stem plot. All right. So a quick review of stem plots. Stem plots, therefore, quantitative variables. The stem can represent the number of tens, hundreds, thousands, etc. We can kind of play around with what that stem represents as far as value. In the same way, we can kind of manipulate the leaves as well. The leaf can represent the second digit or another digit of the number. You need a key. In these 3 examples, we have a key that tells us how to read the stem plot. You must have that. Sorry guys, my cat's been trying to turn my computer off. Go away. Go away. Tries to jump behind my computer and she turns it off sometimes. Bad. Alright, so again, you need a key to read the stem plot and interpret the values, which is represented here, like 2, 2 in this case, represents a male student with 22 pairs of shoes. Right? We're relating what this is for the context. Numbers cannot be skipped in the stem. Just like on a number line when we're making a dot plot, if I have values between 0 and 10, but I don't use the numbers 5 and 6, I don't write the number line as 0, 1, 2, 3, 4, 7, 8, 9, 10, and skip 5 and 6 because I don't use them. I still have to list them because it provides the spacing to have the shape come out properly, right? Same thing in stem plots. I cannot skip numbers. So like in the first one, in A here, right, we have values of 5, 5, 5, 6, 7, 7, 7, 7, 8, 10, 10, 10, 10, 11, 12, 14, 22, 35, and 38. Each of my stems is used at least once, so there's no reason to even think we might skip one. When we go to part B, right, we're doing a split stem where I'm splitting the stems in half. So there's 2 zeros, 2 ones, 2 twos, and 2 threes. And the first row for zeros gets all of the values from 0 to 4, as far as the second digit. And then the second row gets all the values from 5 to 9, right? And so that's how we use a split stem. In this case, if we notice right here at the second one, right, there's no values there, but I don't skip it. I have to include it for spacing, right? Just because I didn't use it doesn't mean it doesn't exist. It just didn't get used. It's an empty space, but I still need it, all right? Same with the first 2, or the second 2, the first 3. I don't have values to go along with that, but I must list it. Right, so this is a common error that I saw on that CYU from week 6. I mean, a lot of you guys, you got that question wrong because you omitted values that you needed for the stem plot. Okay. So anything I can clarify about the stem plots? Does anyone need another moment to write anything down from this page? Okay. Okie-dokie. Next thing that I want to make a comment on about what I've seen in your guys' work, right, is that what you write and how you write it matters. When you're writing your answers to responses, when you're describing things, you know, I've been telling you guys you need to write complete sentences. You got to use good, like, writing skills. Because the graders, the people who grade the AP exam, they care about how you write your answers. You need to be specific and write with good grammar and overall structure. Right? You can't just say, you know, there's 8 numbers. 8 numbers in what? What are we talking about? What's the context? Being specific. All right. We can't just say the spread is 8. We have a bunch of different measures of spread. You need to be more specific. Maybe the range is 8. The IQR could be 8. Right? We have to be specific, and we have to include as much specifics as we can in our writing. Right? You need to say what you mean. Don't leave things up to interpretation. Again, this goes back to being specific. Right? Consider these 2 sentences. One says the range of the numbers is 8. Fine, that is probably what the value is. Right? They probably found the range and it's 8. And then the second response says the range for the height of the players is 8 inches and all the players' heights are between 68 and 76 inches. That gives a lot more detail and specifics. Now I know what we're talking about. We're talking about height. We're talking about players of some sport. Right? We could be more specific if we wanted. We could say football players or basketball players or whoever. Right? We know that the range, we're talking about a specific type of spread. The range for the height is 8 inches, and all the players' heights are between 68 and 76 inches. Now I'm building a picture of what this looks like. What am I talking about? Right? That's necessary. You need to have that kind of specificity in your answers. Right? And, you know, I stress on this because it's important. I know it's a math class, not an English class. However, the people grading this, they're college professors. The people who are grading like the AP exam, they're college professors, or they're like high school teachers who have taught AP stats for years and years and years, and they're part of the grading board or whatever they call those people, right? They don't want to read poorly written responses. They're expecting college level work. That's why you're trying to get college credit, all right? So in any college class, no matter what it is, they expect college level writing. It doesn't matter if it's a math class, a science class, English class, history class, whatever type of class you're taking in college, the expectation is you're writing at a college level, okay? And this is a high stakes, I would consider it a high stakes exam. You know, you only get to take the exam once unless you want to pay to do it again, right? And you could do all the work correct, know how to do everything, find all the numbers, but if you cannot describe it properly and write it properly, you will not pass. You won't get all the points. You won't get all the credit. You're making it harder on yourself. Right? This happened to me personally. I had a high stakes exam that I had to take to finish my teaching credential, and I did everything right. I had all the right content. I had videos. I had, you know, examples of my work, all this stuff that I needed, all the key components, but my writing wasn't done the way that they wanted it. All right? I wasn't flowery enough in my writing. I was just very, for lack of a better term, mathematic in my writing. And for that reason and that reason alone, I had to resubmit sections of this exam and pay like another $300 because everything you do as a teacher costs money. All because I needed to make my writing sound better. I didn't add any extra content. I didn't add any extra numbers, so to say. Everything I needed was in there. I just had to make it sound better and add those extra details and specifics. So I stress on this because it's personal to me. It has affected me. And I know it's out there, and I know that you guys need to be ready for it. So I'm just going to keep stressing on you guys. Please write in full sentences. Write complete sentences. Use good grammar. Be specific, right? So it's going to keep coming up. We're trying to practice this skill, right? Lastly, normal versus symmetric. When you're describing a quantitative variable and its distribution on a graph, if it looks symmetric, say that it's symmetric. We are not calling things normal. This is an error in how the lower level math classes in the textbook that we use addresses things. There are only special distributions that are considered normal. They have to meet special conditions, and we haven't talked about those yet. So up to now, we cannot use that term. It's off limits. We'll cover normal distributions in the next chapter, and we'll find out what needs to happen so we can say something is approximately normal. But for now, if it looks symmetric, or even if it looks normal, based on what you know from previous classes, we're going to call it symmetric. Right? Certain things need to happen to be able to say a distribution is approximately normal. We haven't covered it yet. So for now, you say it's roughly symmetric, approximately symmetric. That's it. And that just means that it looks like it's, if I fold it in half, it's going to be equal on each side. Right? That's as best as we can do up to now. What questions do you guys have? Okie dokie. So now, we're going to skip to our example for standard deviation. So if you're going to be taking notes, now is a good time to get those out. We're going to talk about standard deviation. Alrighty, so in our last class, we already talked about the definitions for standard deviation. Standard deviation is another way of measuring spread. All right? Standard deviation and the variance measure spread by looking at how far the observations are from their mean. So this is a way of measuring spread based on the mean. We already talked about a way to measure spread based on the median, which is our other measure of center, and that's using the IQR, quartiles, right? That's another way of measuring the spread. So we have one way to measure spread based on the median. Now we're looking at a way to measure the spread based on the mean. Right? So here's our definition with a just terrible looking pair of equations, but we'll dissect these, we'll know exactly what they mean. So the standard deviation, S sub x, and variance, S sub x squared. Right? Standard deviation, S sub x, measures the typical distance of the values in a distribution from the mean. Right? The typical distance. Usually when you see that word typical in statistics, you're thinking average distance. Right? It is calculated by finding an average of the squared deviations and then taking the square root. This average squared deviation is called the variance. In symbols, the variance, S sub x squared, is given by this mess of stuff. Right? But all this is saying is you take an observation, subtract the mean, square it, then add the next observation minus the mean squared, then add the next observation minus the mean squared, up until you've used all your observations, or all the numbers. An observation is a number in your data set. You've used all your numbers in your data set to find all the differences squared of the mean, right? Differences and all that stuff. And you divide by n minus 1. Right? We're dividing by 1 less than the number of items in my data set because this accounts for the fact that we're dealing with a sample and not the actual population. If we were finding the variance and standard deviation of a population and we knew the actual mean, then we would just divide by n. But because we don't know the mean of the population, we only have the mean of a sample, we divide by n minus 1 to account for that slight amount that we might be off in our calculation because we don't have the entire population. Okay? So that's the variance. Standard deviation is given by S sub x equals the square root of the variance. This down here is just this equation that was to the right of the equal sign here. So that's all well and good. We have this crazy looking formula, but what does it look like when we actually use it? That's what we're going to do next. All right, so we're going to go through these steps on finding the standard deviation. Before we can do any of these steps, right, we need the mean. We don't have that yet, so we're going to find it. All right. So here we go. We have a number of pets owned by 9 kids. They've already been arranged from lowest to highest for us. So 5, 7, 8, 9. And we're going to use this data to practice finding our standard deviation. Right. First, we're just going to make a dot plot so we have an idea of what this distribution looks like. Right. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll do some dots. We got 1 dot at 1, dot at 3, 3 dot at 4, 1 dot at 5, none at 6, 1 at 7, 8, and 9. All right, here's our dot plot. Not a very interesting dot plot. We only have one value that has more than 1 dot, but now we know kind of what things look like. So now we need to find the mean. We'll use our notation for this. We're going to say, okay, I'm finding x bar. That's going to be the sum of my data points divided by 9, because I have 9 of them. So I'll have 1 plus 3 plus 4 plus 4 plus 4 plus 5, 8, and 9, divided by 9. And this will equal 4 by 16, 21, 8, 66, 45, divided by 9, equals 5. So this is the mean. Right? So that means on average, these kids in our sample have 5 pets, right? And it also means that we could say right here is the balance point, right? Right at 5. All right, so we have our mean. Now, we need to find the distance of each observation from the mean and square each of these distances. All right, so to do this and keep track of this, what we're going to do is going to make a little table. And so first we'll have observation. That'll be in our first column. We will have the distance from the mean. And we'll have the distance from the mean squared. All right, and I'll just write my observations here. I have 1, 3, 3 fourths, 5, 7, 8, and 9. Our distance from the mean is going to be 1 minus 5. We have negative 4. Negative 4 squared is 16. 3 minus 5 is negative 2. Negative 2 squared is 4. 4 minus 5 is negative 1. Negative 1 squared is 1. And no reason to do that calculation again and again. Then we have 5 minus 5, 0. 0 squared is 0. 7 minus 5 2. 2 squared is 4. And lastly, we have our 9 minus 5, 4. 2 squared equals 16. All right. So this here is essentially the numbers that go on the top of this equation. I'm going to add all these up and divide by n minus 1, right? That's step 2. Average the distances by dividing their sum by n minus 1. So this is now, we're finding the variance. Okay, that is the s of x squared. We're going to add all these numbers up. We have 16 plus 4, 1, 1, 1, 0, 4, 9, 16. And we'll have 9 minus 1 to divide by. And this is 20, 30, math today. 20, 23, 27, 56, 52, 52. We have 52 divided by 8. So that we'll double check it on our calculator. And we get 6.5. And this number is the variance. The last thing here, right, is find the standard deviation is the square root of the average of squared distances. We don't need to use this weird looking formula, right? We already have the variance. So that means s of x equals square root of 6.5, which, because I did it earlier, is approximately, not exactly, but it is approximately 2.55. All right? So our standard deviation, 2.55. And we did that just by following our steps here. The reason this formula looks so weird and crazy is because it's done entirely using placeholders, right? We're using variables to represent numbers that, because it's just a general form of the rule, we don't have those numbers, okay? But when we kind of organize it, we find the mean, right? And then we find the squared distance from the mean, add them all up, divide by n minus 1, we get a variance. We take the square root of the variance, we have our standard deviation. And we just kind of follow the process and it kind of works out. So here we have our standard deviation. Right, and so what this means, right, because this has a context that goes with it, all right, is so based on our context, right, we can say I cannot write today, typical. Here's that word typical again. It's essentially taking the place of average. Let's say typical distance of the values from the mean is approximately 2.55, which in this case means that the typical, that word again, number of pets varies from the mean by about 2.55 pets. And it's just a way of describing how spread out the data is again. Right? The smaller the standard deviation, the less spread out our data is. The bigger the standard deviation, the more spread out our data is. So that's really what it tells us. So 2.55, right? That means typically most of these kids are within 2.55 pets of the mean. Okay. We can also use the standard deviation to find outliers. All right. And I'm just going to mention this. It's not something we're going to use right now. So when it is something that we're using, we'll go into more detail. But, you know, possible outliers are greater than two standard deviations above the mean, or less than two standard deviations below the mean. So just like we use that 1.5 times IQR with our quartiles, and we add that number to the quartile 3 and we subtract from quartile 1, anything greater than that added to Q3 is an outlier. Anything less than that number subtracted from Q1 is an outlier. This gives us a similar set of boundaries to say anything outside these points or these values is an outlier. In this example, we don't have any possible outliers based on this because we have, essentially 2.5. 2.5 times 2 is 5. When I add 5 to the mean of 5, I get 10. I have no values greater than 10. I subtract from 5, I get 0. I have no values less than 0. So within this data set, using the standard deviation to rule out or find outliers, we have no possible outliers in this case. All right. What questions do you have? What can I clarify or explain in more detail? Can you raise your hand if you need another moment to write stuff down? Alrighty. In that case, I'm going to jump back to PowerPoint. Pick up where we left off. Good. All right, and last thing I wanted to briefly go over is how to organize statistics problems. This is a 4-step process. And we have state, plan, do, conclude. Right? State, what's the question you're trying to answer. Right? Whenever you read a problem, that's the first thing that should go through your head. What am I actually trying to answer? Right? Identify that first. I know it sounds silly. It's like, well, it should be obvious. It's not always obvious. Sometimes there's a lot of words going on in the context and lots of possibilities of things you could do with that data. But you want to try to limit that based on the answer. Okay, so then the next step is plan. How will you go about answering the question? What statistical techniques does this problem call for? Do you need to make a graph? Do you need to find the median or find the mean? Do you need to find a marginal distribution or a conditional distribution? Right? What kind of data, what kind of things am I trying to pull from my data set or from my variables? Am I comparing two data sets? Am I comparing two quantitative variables or two categorical variables? What am I being asked to do? What do I need to do to get an answer? Make graphs and carry out needed calculations, right? We've planned, we know what we need. Now we're going to do that stuff. And conclude, give your conclusion in the setting of the real world problem. Most of the problems are going to have a context, in which case you now need to take all this data you just sifted through and created these graphs and tables and numbers and write that descriptive paragraph about what the conclusion is. You may need to include, shape, center, and spread. You might need to, talk about how one is greater in this area than another. What kind of inference can you make? What kind of, we're getting into like correlations, right? What things can I say about this data, right? And make sure that those things have the kind of end of answering the question. Right? Don't do a ton of work that doesn't answer the question. Do what's necessary. And be specific, but also be to the point. Right? There's an example in the text. It's who texts more, males or females. It's on page 65 and 66 of the textbook. If you'd like to see an example of like the textbook actually pointing out each of these steps in the 4-step process. Okay. Does anyone need a moment to write anything down from the screen? Mm-hmm. Alrighty. So that brings me to the last part of this. I don't have that right screen at all. Alright, so this week's module is almost entirely done. I just need to do one last thing. We're in week 8. All right, we will be finishing chapter 1. That's what we did today. We'll be starting chapter 2 on Thursday. I'll be updating the live class resources later today to include the PowerPoint and the notes, and also the recording of this live class session. We have a discussion board here. This has to do with standard deviation and a context. Do not worry, there's only like 5 numbers in this data set, so it is entirely possible to do by hand. Then we're going to be talking about modeling distributions in chapter 2. We're starting with percentiles. You may or may not remember percentiles from previous math courses. If you don't, do not worry, we'll cover it. And then lastly, because we are finishing chapter 1, the kind of weekly assignment this week is the chapter 1 self-assessment. I have not put this together quite yet. It's going to be very similar to the chapter 4 self-assessment as far as structure. There will be a main question as far as a demonstration of understanding to kind of put everything together that we've done in this chapter. And you'll, give me some feedback, things that would have helped you, that reflection part. And you will self-assess and tell me what grade level you feel your understanding is at this point. Okay? Remember, the self-assessment is weighted more than the other things. So if you're at a place where you need to choose which assignment to do this week, all right, choose the self-assessment. It's worth more. All right. Remember, all the due dates are just loose. I have the 2 discussion boards set up to be due on the 19th, which is next Monday. The self-assessment will not have a due date until next Friday. All right, so you'll have a little over a week to work on that from the time that it gets posted. I like to give you guys more time on that because it should involve a little more work. All right, so that's what our week looks like. Are there any questions about this week? All right. So if there are no questions and there's nothing else I can help you with today, that's the entirety of the lesson. We are done with chapter 1. We're moving on to chapter 2 on Thursday. If you have any questions, need some help on something, please feel free to stick around in this meeting and ask. Otherwise, you can email me or send me a message through Canvas, send me a message through Teams, and I will help you. Other than that, have a wonderful day, and I will see you on Thursday.